Well, thank you. It's a real honor to be here. This is my first time in Kansas, and I've been driving around the state the last few days and seeing what a truly emerald state it is. I've been noticing emerald things everywhere. So tonight I want to talk to you about a project that, as Amy mentioned, my sister and I have been doing together for the last 7 or 8 years. We're crocheting a coral reef. But before I launch into the story of the reef itself, I'd just like to spend a few minutes discussing the wider context in which we do this project. My sister Christine and I are co-founders of a non-profit organization in Los Angeles called the Institute for Figuring. And the Institute is a rather unusual organization in that what we seek to do is to enhance the public appreciation of the aesthetic and poetic dimensions of science and mathematics. So what we are interested in doing is encouraging people to literally play with ideas. We often think about science and mathematics as subjects that are taught through textbooks by studying equations and formula. We think about these as it were, symbolic activities. But Christine and I believe that ideas can also, or many ideas, scientific ideas, can also be embodied in material objects, and that by literally playing with ideas, you can often come to a deep understanding of these subjects. One way we think about the Institute for Figuring is that it's a play tank, and you all know the term think tank. So think tanks are places where very smart people go and they think ideas and they write books and they write op-ed pieces and they try to influence public opinions about various ideas. Well, Chrissy and I believe that we also need places where people can come to play with ideas, and that's what we think the Institute for Figuring is trying to do. One of the things that we're very, very specifically interested in is the way that ideas can be embodied in material forms. And much of what we do is about trying to engage with ideas by encouraging our audience and our visitors to make things for themselves, from simple materials such as paper, by cutting and folding paper, by folding business cards together, and by simple, humble craft activities such as crochet. One way you can think about this is that it's kindergarten for grown-ups. So, as a matter of sort of concrete practicality, what we do is we have a very large website for those of you who might be interested, and I've also just bought some of we have a nice little card to introduce the IFF, so those of you who might be interested, let's take one of those later. So we have a very large website where we have online exhibitions and a lot of information about our activities. In terms of activities, we host a lot of workshops and lectures, but increasingly what we're known for is doing exhibitions. We've done exhibitions with many, many other institutions, including the Smithsonian, the Hayward Gallery in London, the Science Gallery in Dublin, the Scottsdale Civic Centre in Arizona, the Chicago Cultural Centre. So we work both with science museums and art galleries to craft exhibitions which usually have a large-scale participatory dimension to them, like the Crocheted Coral Reef project, which I'm going to talk about in a moment. And last year, we finally realized a long-term dream and opened our own exhibition space in LA. It's a small space, but it gives us the opportunity to experiment with ideas that we might like to do later on a bigger scale. So any of you who come to Los Angeles, please come and visit us. We're in the Chinatown district of LA, which is booming at the moment as a place for innovative, interesting, experimental art galleries. What the IFF is most well known for is our Crocheted Coral Reef project. And as I said earlier, this is a project that Christine and I started. It was in Christmas of 2005 when we began the project. And to our surprise, it has blossomed from our living room to become a worldwide phenomenon. We didn't really imagine creating a worldwide phenomenon. In fact, when we started the project, we imagined that there might be 20 or 30 other people who were interested like us in this sort of quirky intersection of art, science, and environmentalism. But to our surprise, it has gradually sort of escalated, and now there are people all over the world doing this. We've had exhibitions of the project in many, many different places, and I'm just showing you here a few of the images of what the exhibitions look like. And as you see, it has morphed now that there in fact is not one crochet coral reef, but many different crochet coral reefs, because what we gradually found as we were doing that, like any artistic project that has a life of its own, it begins to sort of develop in its own ways. And one of the things that it has, one of its developmental aspects is that there have come to be different coloured reefs, and particularly there are two white reefs which represent the phenomena of coral bleaching. Corals, as you probably know, indicate that they're in a state of stress or illness when they go white, and I'll talk in a moment about why that happens. So here we have an image with some of the white ones at the front and the very healthy, colourful ones at the back. So I just want to give you a sense of the scale and the scope of this. And each of these individual reefs involves hundreds, if not thousands, of different pieces. To give you an idea of scale, this was our first large-scale exhibition at the Chicago Cultural Center, and that's actually a photo of we arranged them this time in a large ring-shaped formation to represent a coral atoll, and that was about 15 feet in diameter. So there were probably several thousand individual crochet pieces that go to make up that reef. The project has been through various phases, and this was part of our sort of early, what we call realist phase. So during one of our first goals was to try to produce reefs crochet reefs that actually really looked like living reefs. And gradually, as the project has evolved, we've kind of got more fantastical and surreal, so that there are all of these different reefs that have kind of different aesthetics, but one is never in any doubt that one is actually looking at something that's a representation of a reef. For those of you who've been scuba diving, there's no reef on planet Earth that's anywhere near this colourful. Reefs actually are often quite muted in colours, but these shapes, these crenellated frilly forms which you can mimic so easily in crochet, so evoke corals in our minds that it's sort of almost any colours and any kind of configurations that you do of these frilly sculptural things tends to evoke the phenomena of a reef psychologically. We've done them, as I said, all over the world, and this was the biggest one that's ever been made, which was done last year in Germany in a wonderful museum on the island of Föhr, which is a little island off the coast of Germany, between Germany and Denmark. And 700 women all over Germany and Denmark, and people as far away as Holland and Luxembourg, contributed to this installation. The other really enormous one that we've done was at the Smithsonian's National Museum of Natural History. And here, as you can see, we've gone very wild. One of the forces, the aesthetic forces that Christine and I are always trying to channel through this project is Cat in the Hat. We both grew up in love with Dr. Seuss, and Cat in the Hat has definitely been one of the great aesthetic forces in our artistic lives. So as the project has progressed, one of the things that's happened is it sort of mimicked the evolution of life on Earth. So the early installations were very sort of very flat and low. And just as life on Earth begins with pond scum and gradually evolves upwards towards redwoods, so too our project has been through an evolutionary project of gradually going onward and upward and bigger in scale. So why are we doing this? Well, the big inspiration why we wanted to actually crochet a coral reef was because about the time that we started the project in 2005, that was the year that there began to be a lot of stories in the press, in the science press, about how coral reefs were being devastated by global warming. Coral reefs have been under stress for a very long time due to things like overfishing, over-tourism, sewage runoff, toxic waste dumping in the oceans. And my sister and I grew up in the state of Queensland, Australia, which is where the Great Barrier Reef is. So the corals and the plight of them weighs heavily on the consciousness of all Queenslanders and all Australians. And we were all aware of the stresses, but corals in recent years have been experiencing these very great bleaching events on a much more devastating scale and with much more frequency than they used to happen, say, when I was a child. And about 10 years ago, scientists began to realize it was because, in addition to all of the traditional stresses, that they were being stressed also by the fact that the sea temperatures were rising. So these bleaching events where the corals lose all their colour and go white are indications that they're sick. And if the conditions return to normal, they will get back their colour and be healthy again. But if the conditions stay bad, they will ultimately go completely white and die. And the Great Barrier Reef has now had massive coral bleaching on about a third of its area. The Barrier Reef is the largest living organism on Earth. It's the first living thing you can see approaching Earth from outer space. And the fact that it's having these massive bleaching events is proof that global warming is not something in the future. It's here now, and it's devastating corals. But it turns out that there is another problem due to the CO2 in the atmosphere that's even worse for corals than the warming of the sea. And that is the fact that a lot of the carbon dioxide in the atmosphere will ultimately get absorbed into the oceans. About a third of it ultimately gets absorbed. And your first thought is, well, that's really good. It takes it out of the atmosphere. But the problem is that what the CO2 does in the ocean is it turns it more acidic. So much so that scientists are beginning to talk about the Coca-Cola ocean. And what this increasing acidity does is it prevents the corals from forming the bony structures that make the reefs. It doesn't actually kill the organisms. Coral organisms, the little tiny polyps they're called, are like little miniature jellyfish. But when they come together collectively, they can build these rigid bony structures that ultimately become the giant topographic forms of the coral reefs. And the acidity increasing the acidity of the ocean so changes the basic chemistry of the sea that it prevents them from forming these structures. And the problem is now so bad that scientists predict it's entirely possible that by 2030 the oceans will be so acidic that coral organisms will no longer be able to form these bony structures at all. It's estimated by scientists that if the CO2 concentration in the atmosphere goes beyond 480 parts per million, that the acidity will be so great that corals will not be able to form this basic function, and we're fast approaching that. So Chrissy and I decided that we would crochet a coral reef as a sort of artistic homage to the living wonder of natural corals. And in 2005, we joked to ourselves that if the Great Barrier Reef ever died out, there'd be something to remember it by. In 2005, that was a joke. But in 2013, scientists are actually beginning to talk about the possibility that that might actually happen. So the question arises, if you want to make an artistic representation of a reef, why on earth are you crocheting it? You know, why not chisel it in stone or paint it? But it turns out there's actually a logically necessary reason why we are crocheting. It's not an artistic choice. It's almost actually the only scientifically, it's the choice that has the most scientific integrity. And that is because if you look at the frilly crenellated structures here that we're making with crochet, what they are is they're manifestations of a kind of geometry called hyperbolic geometry. And all of these organisms on coral reefs that have these frilly, wavy forms, they are biological manifestations of this hyperbolic geometry. So corals, sponges, kelps, sea slugs, nudibranchs, all those frilly, roughly formed organisms, they are actually manifesting a kind of geometry that is an alternative to the Euclidean geometry that we all learn at school. So here's crochet ones, and here's some real corals. And you see the wavy, crenellated forms. These are natural manifestations of hyperbolic space. So these are corals and sponges, and then you can see them in some nudibranchs. And it turns out that nature actually has a love affair with hyperbolic geometry. It's a funny thing that human beings, in fact great mathematicians, had literally spent hundreds of years trying to prove that hyperbolic geometry was impossible, because it violated a basic premise of Euclidean geometry, and mathematicians didn't believe that that was possible. But here's two creatures who've never heard about the axioms of Euclidean geometry, who are just happily getting on with it. So it's a funny thing that sometimes when I talk about this project, I say that the goal of my talk is to get us all up to the level of a sea slug. That in some sense, the sea slug knows this mathematics. And it's kind of an interesting thing to me, you know. Here's two little chaps that have barely got a brain. And they're manifesting in the very structure of their being a kind of mathematics that literally the greatest mathematicians of Western culture did not believe was possible. So it kind of raises an interesting question: what does it mean to know? And who knows and what knows? And I would claim that in some sense they know. So what is it that they know that we'd all like to know? And I should point out that the reason that we're crocheting this is because this almost impossible mathematics is quite apart from what the mathematicians thinking that was mathematically impossible. Even once they found out it was mathematically impossible, they didn't know how to make models of it. And it was only in 1997 when a Latvian mathematician named Dr. Daina Taimina, who was at that time at Cornell, she discovered that you could make models of this with crochet. And that was a real surprise to the mathematical world, who up till that time didn't really have a way of making models of these things. So Dinah, with her crochet, showed that basically with a feminine handicraft, you could make models of this almost impossible space. So what is this impossible mathematics? Well, you're about to learn that you all know a lot more geometry than you think you do, and you're also capable of knowing a lot more higher geometry than you probably give yourself credit for. At school, we all learn about Euclidean geometry. At least I hope kids still learn Euclidean geometry. And you're all that's the geometry of a flat surface, like a piece of paper or a tabletop. But you're all pretty familiar with another kind of geometry, which is spherical geometry, the geometry that exists on the surface of a sphere. And the reason that spherical geometry has been studied a great deal is because of the surface of the Earth. We live on the surface of a sphere, and understanding spherical geometry has been incredibly important for astronomy and for navigation. And it turns out there is actually a third alternative, which is hyperbolic geometry. And hyperbolic geometry can be conceived of as the geometric opposite of spherical geometry. So hyperbolic space is the geometrical opposite of spherical space. Now, what does that mean? It's okay if you're a bit bamboozled at this point, because the mathematicians who discovered this were highly bamboozled. And it took them literally hundreds of years to overcome 2,000 years of prejudice to get over this. So it's okay. I want you to be a little bit bamboozled, because when you understand, it's beautiful. So one way of understanding this is to think about the curvature of all of these spaces. So if you think about a flat plane, piece of paper, that has 0 curvature. It's the same all over. And a sphere can be conceived of as having positive curvature. Now, just as there are positive numbers, 0, and negative numbers, so too it makes sense, doesn't it, that if there's positive curvature and 0 curvature, there should be something called negative curvature. And so there is. And that is what hyperbolic geometry is. It's the geometric equivalent of negative numbers. And it's okay to think, how could that be? Because mathematicians thought, how could that be? But mathematicians had the same problem when they originally encountered the possibility of negative numbers. What did a negative number mean? And that was actually a big revolution in the history of mathematics, to accept that if you've got 0 and you've got something on this side of it, you should also have something on that side of it. What does a negative number mean? And actually, it's very interesting why mathematicians actually came to accept negative numbers. Although it seemed an absurdity, how could you have -3 oranges or -3 apples? But the reason the negative numbers became accepted in the history of mathematics was because of finance, because everybody understood what it meant to have negative $3. It's called being in debt. And that actually is the historical reason why the negative numbers actually entered mathematical consciousness to deal with accounting. So negative numbers were difficult for mathematicians to accept, but the practical problem of accounting brought it into being. With negative curvature space, it wasn't at all, when mathematicians first encountered that idea in the late 18th century, their minds resisted it because they didn't have any concrete physical situation to attach it to. So they just sort of had to take it on faith because the mathematics sort of mandated the same thing. If you've got a 0 and a positive, it makes logical sense that there's a negative. But what is this negative? So we're going to get to that in a minute, but this is the way mathematicians had to go through this process. So how can we understand this? Well, there are a number of different ways, but one really lovely way of understanding it is the following. You can think of different geometries in terms of how I can tile a plane, how I can fill the whole space with little shapes. So this represents how we can tile a Euclidean space, a flat space. You can fill it with hexagons, and you all know this because this is the beehive structure. So we can fill a plane with hexagons and have no gaps. Now, what happens if I take some of the hexagons, which each of those have 6 sides, and I replace some of them with pentagons, which have 5 sides? So I'm actually going to take away some of the sides, and I get a structure that you all know. And does anyone want to guess what it is? Very good. It's a soccer ball. And so this is like an approximation of a sphere. So by taking away, by going from the Euclidean case where we take away some sides, we move to the sphere, the space closes in on itself. So it makes sense that if I can take away some sides and make the space close in on itself, I could do the opposite. I could put in some extra sides and therefore add space into the equation. So that's what I do to make hyperbolic space. I take the 6-sided ones, and this time, instead of replacing some of them with 5-sided ones, I replace them with a 7-sided one, and what I get is the geometric opposite of a sphere, and it's called the hyperbolic plane, because it's got all this extra space in it. That's where the word hyperbolic comes from. It's got all these extra bits to it. And so here's one. I can actually make a paper representation of it, and here is a really elaborate one. You can't, so this is an approximation, and these are beautiful to make, but very fiddly and very difficult to deal with. And it's really interesting. The paper really doesn't want to go into this hyperbolic. It really resists. You're trying to force Euclidean paper to go into non-Euclidean structures, and it really resists it. So you have to work. I got some of my students to make this, and it was really elaborate. But it's so much easier to do it with crochet. It's really easy. With crochet, it's very simple. You just crochet along and you add stitches. So just like when we move from the Euclidean case to the hyperbolic space by adding sides, you just add stitches in. You just simply increase. So Dr. Taimina realized that she could model hyperbolic space simply by increasing the crochet stitches. Now, what this means is that every woman who's been crocheting ruffles for hundreds of years has been crocheting hyperbolic geometry, and they just didn't realize it. And ballerina skirts and some peasant, gypsy skirts, which are made up from circles all linked together, they too are hyperbolic. So women with these traditional handicrafts have actually been making hyperbolic structures for a very long time. And one of the things that's beautiful about this is with these woolly crocheted hyperbolic surfaces, you can stitch theorems about mathematics, you can stitch the mathematical theorems onto the surface. But you can stitch theorems onto the surface of these models and prove that because the behavior of lines and triangles and circles is different on a hyperbolic plane than it is on a Euclidean plane. And when I learned this, when I learned about hyperbolic geometry at university, we just had to learn this kind of theoretically and symbolically, and it was really difficult to understand what was going on. But when you do it with crochet, you can hold these things in your hand and you can see the actual principles. And what this here in wool is proof that the most famous axiom in mathematics, Euclid's parallel postulate, is wrong. And this was one of the foundational moments in the history of mathematics in the early 19th century when mathematicians realized that one of Euclid's axioms was wrong, or at least it didn't always hold. And here for the first time, when Dr. Dinah Taimina made these, you could hold it in your hands and see for yourself. And the introduction of hyperbolic geometry was incredibly important in the history of mathematics because it opened up, exploded the whole field of geometry and introduced what's called non-Euclidean geometry as a whole new field of mathematics. And it is the study of non-Euclidean geometry, which is the mathematics that underlies general relativity, which is the mathematics that will ultimately tell us about the structure of our universe. So one of the things that I love about this is that it shows you that here we have feminine handicraft, the structure of sea slugs and corals, and the structure of the universe. And these things are linked together through this beautiful feminine handicraft. And it suggests to me that we are used to pigeonholing things and putting the marine biologists over here and the cosmologists over here and the women with their little handicrafts over here. But these things are actually linked together and not necessarily as far apart as we're sometimes led to believe. But the Crocheted Coral Reef project actually really began when we realized that we didn't have to stick to doing mathematically perfect ones. This is a mathematically perfect ones, and the few that I've passed around are also mathematically perfect. But when you do it, the precise mathematical algorithm, there's only a limited number of forms you can get. But once you start to get a little bit wonky, when you don't increase at exactly the same rate, when you introduce deviations and aberrations, the forms immediately begin to get more natural. And it was my sister Chrissy, who comes from an art background, who one day came home and she said, you know, I'm sick of doing mathematically pure ones. I'm going to branch out. I'm going to be wonky. And she came home one day from the yarn store with these big bag of sparkly, glittery, fluffy yarns. And she said, I'm going to go wonky. And me coming from a science background, I said, oh, no, we shouldn't do that. And she said, you know what, get over it. And she started doing these aberrant ones, and they immediately began to look natural. And it was because nature is wonky. Nature doesn't stick to the formula. There's no such thing in nature as a perfect sphere. There are lots of things in nature that are sphere-like, like eggs and sea urchins, but there's no such thing as a perfect sphere. And so too, there's no such thing in nature as a perfect hyperbolic. Nature loves aberration, it loves deviation, it loves to be wonky. And so we started exploring. We started, as it were, like we started on an evolutionary process. What would happen if we morphed the code? if we introduce deliberately deviations. And what we gradually discovered is that there's an entire taxonomy of crochet coral species. And to our surprise, we've come to believe that just as there is no, as it were, end to the diversity of life on Earth, so too there is no end to the diversity of the crochet coral tree of life. And over the years, we've been invited to do this project at many different museums, from Chicago, the Chicago Cultural Center, to NYU, to the Hayward Gallery in London. And one of the beautiful things that has allowed the project to become so big is that very early on, we started to work with the communities. So when we had our first big exhibition in Chicago, we worked with the community in Chicago, and hundreds of people in Chicago. We taught them the techniques, and then they taught their friends, and workshops were held over a period of about 6 months. And the people of Chicago produced a reef. And then the people of New York produced a reef, and London. And then people wanted to start doing it all over the world in other places where we weren't even exhibiting, like Sydney and Latvia and Oslo. And there have now been more than 25 of these reefs made all over the world. And there's been more than 7,000 people have contributed to these crochet coral installations. And one of the things I'm most proud of about the project is that in this sense, it mimics the coral organisms themselves. Coral polyps, as an individual organism, is a tiny little thing about this big. The coral polyps, they're like very primitive jellyfish, and they float around in the sea, and each little individual coral polyp has very little power and no brain. But when they come together, hundreds or thousands of them come together, they form a head of coral, and together they grow a primitive vascular system and a primitive digestive system, and they become an organism that starts to build this beautiful structure. And when billions of them come together, they build the Great Barrier Reef. And so too, the Crochet Coral Reef project, this is the Smithsonian reef, is a collective project. These reefs are beyond what any individual human being could do on their own, but they show what humans can do collectively together. It is the work of thousands of people that produce these things. And to me, the lesson here is that I think, like corals, we humans are individually insignificant and not very powerful, but together we can do extraordinary things. So these are just some of the images of some of the reefs that have been produced. And the project has engaged people from all walks of life. These are some of the people from Latvia. I love this picture. It's so sort of post-Soviet. But the people who have done this come from all walks of life. There have been scientists, mathematicians, students, high school students, inmates of the Indiana State Women's Prison. There's currently starting up in a prison for girls in Denver, for girls who are incarcerated because they got trapped in gang violence, are doing a reef in a prison in Denver. We've had children, grandmothers, women who are professional artists from all walks of life. And they each have amazing stories. This woman here, her name is Kathleen Greco, and she's an industrial designer who's an absolutely wonderful crocheter. And she invented this thread. It's a special vinyl thread that she invented to crochet and knit with, because there wasn't any vinyl, there wasn't any plastic thread on the market that you could crochet with. And why is she putting it in the oven? It's because when you put it to bake on a low temperature, it softens the material, it softens it and makes the crocheted item more flowy like a fabric. And Each of our contributors has an amazing story. This woman, Helen Bernasconi, is a former computer scientist who left being a computer scientist and went to live in rural Australia, where she now has a little sheep farm. And she grows the sheep, shears the sheep, spins the wool, dyes the wool, and has made these extraordinary crochet, this huge crochet. We call this our sea snake. And all of our women have produced amazing objects and each have their own stories. I should say the one common thread in the project, to our surprise, is that of the more than 7,000 contributors, 99.99% of them have been men. We have had a few men, but very few. And that's actually surprised us. I did not expect that so many of the contributors would be men. But what we have found is that collectively, the community has created, as it were, an ever-evolving crochet tree of life. It's as if Chrissy and I sort of punctured a hole to a parallel universe of untapped creative feminine energy. And the question that I think this project raises is, all this has been done with no major institutional support. There is out there an enormous world of untapped, skillful, loving, creative, feminine energy. What could happen if it was truly tapped? So I just want to end by showing you a little slideshow of some of the most extraordinary works done by our contributors. And it is proof, I think, that ordinary people can do extraordinary things, and that collectively we humans could also do the extraordinary and heal our planet if we work together. And I'll just end on this piece. This is the only piece that we have that has electricity whizzing through it. And it's made out of a kind of material, it's called electroluminescent wire. And it's kind of wire with a plastic coating on it. When the current flows through it, the plastic fluoresces. It was a product that was made for the US military. It's used to light the insides of tanks and also to lay out military airfields in remote places like Iraq. And our contributor, Eleanor Kent, who's our oldest contributor, she's now an 85-year-old grandmother who's also a media artist, decided that she wanted to take this military hardware and repurpose it into a crochet coral. So it is a truly bioluminescent sea creature. And I think it's an extraordinary testimony to the creativity and wonderment that ordinary people can produce when given the opportunity. So I hope this project can serve as an inspiration to people everywhere to think about what we humans can achieve if we truly wanted to put our minds to it collectively, like corals working together. So thank you very much.